Yay!
Yay! Let's take a look at how we can use some of the basic physics we've done so far to get, I don't know, sort of a peek into a larger, beautiful room of physics. So let's use what we know so far to see if we can talk about some of the beginnings of Einstein's special theory of relativity. And what we're going to be focused on is a really interesting effect that for observers in relative motion, their clocks run at seemingly different rates if we compare them. So let's look and see how we can get sort of a feeling as to how that might arise just using what we know so far. This is usually followed up a lot more in the modern physics class, but we can get a little bit of a sense of it just from what we know. So let's see how this works. Suppose I have two protons and I'm sending them in parallel directions. So they have they're both traveling at the same speed, v, and I send them through, I don't know, some sort of a pipe or something. So they're separated by a distance r. What I want to know is, what's maybe not immediately clear, is what's going to happen to these things as time goes by. If they're both flying by the observer, so this is us in sort of a lab frame, so if they're flying by us with a speed v, what might not be immediately obvious is what's going to happen. I mean, one thing we know for sure, just by looking at it, is that we know that the electric force, Fe, I know that the electric force on A due to B is going to be pointed up, right? They're going to repel each other electrically because they're both positive. So for sure, the force on A due to B, the electric force on A due to B, is going to be pointed up. Now, what about the magnetic force? They're both in motion. So let's look at what is the force, the magnetic force on A due to B. That's a horrible notation, right? Because I'm using B in two different things. That's B is for magnetic fields, but also there's a particle B. I should have called it something else. Anyway, so what is the magnetic force on A due to B? Well, the first thing we have to know is what's the magnetic field at the position of A. What magnetic field does A see? Well, B is moving to the right at a speed v, right? So if B is moving to the right at this speed, it's going to generate a magnetic field at the position of A. And using your right-hand rule, what you know is that magnetic field is going to be coming out of the board, right? So here is, here's our magnetic field, B, of particle B, at the position of A. That magnetic field is coming out of the board, and so that's the magnetic field that A is traveling through, according to us. And what's the force then? Well, if you do your right-hand rule, force is QV cross B. What you find out is the magnetic force is that way. So magnetically, and I don't mean that those arrows are indicating any sort of magnitude, I just had more room below. So anyway, so the thing to take away from this is that those two forces, the electric force and the magnetic force, are in opposite directions. So one thing that you could ask is, which one wins? What's actually going to happen? This looks like an experiment you could actually do. You send two charged particles on parallel tracks, and which force wins? Which force is stronger, the electric force or the magnetic force? Well, it's maybe not obvious which one wins, what's going to be more important. So let's see if we can calculate it. One easy way to do it is we can do a ratio. Let's do a ratio of the magnetic force magnitude compared to the electric force magnitude. So that if the ratio is exactly 1, then the forces balance and these things just continue on parallel tracks, right? If the ratio is less than 1, then that means the electric force has 1. And so particle A is going to be bent upwards and it's going to hit the pipe. And then if it's greater than 1, then the magnetic force wins and these two things are going to collide, right? They're going to kind of be attracted to each other. So let's compute the ratio. Let's see what that is. Okay, so the magnitude of the magnetic force is QVB sine theta, but again, as in most of our other examples, theta is 90, so sine of theta is 1. So this is just going to be, these are just, let's suppose they're just protons, all right? So this is, the charge is just going to be EV times the magnetic field, right? And the electric force is just E times the electric field. Okay, but we know what these things are. We know what the magnetic field and the electric field are. So what is the magnetic field from charge B up there? Well, we said that that was, what's the magnetic field from a point charge? It's mu naught over 4 pi. And then this is going to be Q, which is our E, times V over R squared. And there's a cross product there, but again, the cross product is just going to have a 90-degree angle. So there we go. So there's the magnitude of the magnetic field from the point charge from B at the point of A. And what's the electric field from B? The electric field is just going to be K times Q, which is our E, over R squared. There's the magnitude of the electric field, right, from way back. So there we go. There's our ratio. Now, notice this. All the charges cancel out, so it actually doesn't matter. As long as the charge is the same, it doesn't make any difference what the charge is. And then also, look, the R's cancel out. This is going to get a lot simpler. So it doesn't matter what their original distance is. The magnetic and the electric field both fall off as 1 over R squared, so the distance cancels. That's nice. So our ratio, FB to FE, what do we have left over? It's just mu naught. And I'm going to have a, I'm still going to have my V, and then I'm going to have, oh, V squared, right? There's another V up there. And then I'm going to have my 4 pi times our K. So let's rewrite it. Remember, K I could write in terms of another fundamental thing called epsilon naught. K is 1 over 4 pi epsilon naught. So let's plug that in there. And the nice thing about that is that those 4 pi's are going to cancel, right? So this ratio, FB over FE, is just going to be mu naught epsilon naught V squared. So there's our ratio. Okay, now, if you haven't seen this before, this is going to be a very interesting thing that maybe you haven't anticipated. What is mu naught epsilon naught? Those are, remember, those are fundamental constants relating. Mu naught is related to the magnetic field. Epsilon naught is related to the electric field. If you remember what they are, you have a calculator that's got them wired in. In your calculator, here's an interesting thing that you can do. Take 1 over the square root of mu naught epsilon naught. If you just plug those values in, you get something really interesting when you're done. And what you get is about 3 times 10 to the 8th. And you can verify, if you go back and work through the units, that's going to be units of meters per second. What is 3 times 10 to the 8th meters per second? That's what we call the speed of light, right? And you might say that's equal to, in fact, I'm writing a definition, that's equal to c, the shorthand notation for the speed of light. You might think that's a crazy coincidence. How can 1 over square root of mu naught epsilon naught be so close to the speed of light? Well, this was found by different means that we'll talk about in a subsequent video. This was found by Maxwell back in the late 1800s, and he took the step of noting that it probably was not a coincidence that this combination of fundamental constants was so close to the then observed speed of light. And he just took it to mean that that actually is the speed of light. That defines the speed of light. And why light should suddenly be involved with electric and magnetic fields is tied into his great synthesis of electric and magnetic fields and light and radiation, because what he found ultimately was that there's a very deep and intimate relationship between the two, in that light is nothing other than waving electric and magnetic fields together. And if you haven't seen that before. It's a beautiful thing. So anyway, look at what that means. That means that our ratio, what we have here, FB, the ratio of the strengths of these forces is just V squared over C squared. And that's really interesting. We will show in modern physics later, we'll show that the speed of light, there are good reasons to think that that's sort of a cosmic speed limit. So our V is not going to be greater. We're not going to be able to fire these things faster than the speed of light. So V over C, that's always going to be less than 1 is the point. So if that's always less than 1, then look, the electric field, the force due to the electric field is always going to be stronger than the magnetic force. So always, this implies that always the electric force is greater than the magnetic force. So always what's going to happen is that these two things will repel each other. And so they will hit the sides of the pipe. Okay, that's kind of interesting. So we get an answer. It's definitely true that the electric force is always going to be stronger in this case than the magnetic force. But here's where we can do an interesting thing. Imagine that you're riding along. Suppose you do this experiment. We're watching from the lab. We watch these things fly by. But suppose you've got a friend, and this friend rides along with the charges. Maybe they're riding along on a train, and the charges are just sort of hanging outside the window of the train. So they're in a frame where these charges are at rest. So in the rest frame of the charges, look what happens. And this was Einstein's genius, is to take so many different physical situations and examine them from different frames. If you're traveling along with the charges, their speed is 0, right? In the rest frame, their speed is 0. And notice what that means. If the speed is 0, one of those forces is 0. It's the magnetic force. There is no magnetic force. There is no magnetic field if the particles have no speed, right? They're just static charges in this frame. So in the rest frame, the speed is 0. So the magnetic force is 0. So that means, and look what the magnetic force does. The magnetic force sort of slows down the particles crashing into the side because it's fighting the electric field. Right? So the electric field is making the particles crash into the sides of the pipe. The magnetic force is slowing that down because it's opposite. So in the rest frame of the particles, notice what happens. There is no magnetic force, so there's only the electric force. And so these particles slam into the sides more rapidly. So now we get to it. Let's suppose in the lab, suppose you measure the time taken. The time in the lab is, just for the sake of argument, suppose it takes 2 seconds for these particles to crash into the sides. So they're going to travel, and then they're going to be bent up, boom, and they hit the sides there in 2 seconds, let's say. And that's with the magnetic force fighting the electric force. Well, if then your friend in the rest frame, it's a little confusing to say rest frame, right? Because it's the rest frame that's actually moving with the charges. So that doesn't sound like rest, but understand what that means. That's the rest frame of the charges. So in the rest frame of the charges, you have only the electric force, no magnetic force fighting it. And so this is going to happen faster. And so just for the sake of argument, suppose the speed is such that it's happening twice as fast. So delta t in the rest frame is 1 second. And look what this means. You're seeing the same, 2 different people are seeing the same experiment happen, and they're both using accurate stopwatches, and they're getting 2 different times. And the only difference is that there's relative motion between those 2 frames. One is in the lab, and one is traveling with the particles in the rest frame. So what that tells you is delta t rest counts more slowly. For every 2 seconds that go by in the lab frame, only 1 second goes by in the moving frame, the frame moving with the charges, the rest frame. That's special relativity. That's our first peek into special relativity. The fact that time is going to go at different rates according to the different observers if they compare their rates. All this is a little bit loosely speaking. We'll be a lot more formal about this when we get to modern physics. But it's really interesting. This is our first encounter with the fact that clocks don't run at the same rate if they're in relative motion. So for every, and it doesn't have to be, I mean, you could imagine it's not because of anything having to do with the hearts. 2 heartbeats, it has nothing to do with the clocks. 2 heartbeats might elapse in the lab frame, and 1 heartbeat might elapse for the moving frame. And so in some sense, the person who's traveling along with the charges is going to live a little bit longer because they haven't had as many heartbeats, right? So when you hear loosely speaking that time slows down the faster you travel, this is the kind of thing we're talking about. And again, that's only loosely speaking. We have to actually compare the clocks. But you can say, what we can say right now is that the elapsed times are different for observers in relative motion. Which is just sort of an astounding thing, and it's really cool that we can see that. We can sort of start to explore that just from the basic physics we know. And for those of you who've seen some special relativity, you might also know that the fields of moving charges are modified, and so you might think that we have to be a little bit more careful. But this is a general result because we did the ratio of the 2 forces, and what turns out to happen, again, we'll look at this more carefully when we do modern physics. What turns out to happen is that the electric field is modified by the same factor as the magnetic field, so the ratio stays the same. So it is true that I played a little fast and loose here, saying that talking about the electric field of a moving charge and the electric field of a stationary charge as sort of the same thing, and they're not, but the ratio stays the same. So that's a kind of a neat thing.